Should we talk about the exam now or just wait till the end? Wait till the end? That way, in case people show up late or when people show up late. All right, so last class we kind of wrapped up 8.1. The last thing we talked about was the monotonic, bounded monotonic sequence theorem, right? Kind of showed you how it's kind of strange how we show something is bound or is convergent using that theorem. And now we're going to start 8.2. So I actually like to go off of, I have handwritten notes that I don't hand out to you for this section. And that's because all the problems are worked out, and I want to be able to work them out here and not give away the good stuff, all right? So I'm going to be going off my own notes here today. And I also handed out this sheet. Okay, so if anyone needs a copy of this, I'm just going to put them up here, okay? So are you all ready for 8.2? Okay, this is not on the test, which is on Tuesday. This is not going to be on the test, but just make sure we're keeping up with things. Don't put this off. Okay, you're going to want to do your homework for this right away because it's a pretty heavy assignment. So this section, I believe, is called series, if I'm not mistaken. All right, so I'm going to be putting some definitions up here on the board. The first one is this: a series, or what we will refer to as an infinite series, all right, so when we say series, we are implying that it is an infinite series, is the infinite sum of the terms of a sequence. So we learned last class and the class before what a sequence was, right? A sequence is a list of numbers, right? Yes? And now what we're going to do is we're going to take that list of numbers and start adding them up. Right? So basically, if we have some sequence, a sub n, which is equal to a1, a2, a3, forever, then the series for that sequence is a1 plus a2 plus a3 forever, right? That's what the series is. So to find the series of something, you have to start with a sequence. Start with a sequence. Once you know what the sequence is, then we start adding them all up. All right? So it's an infinite sum, goes on forever, dot, dot, dot. Now, we have a different notation for this. And we saw this when we did Riemann sums. Remember when we did Riemann sums, we had that special sigma notation? So this can also be written as the sum from k equals 1 to infinity of a sub k. Do you agree? So what this is saying is you start with k being 1, you take a sub 1, then you say plus, and then you let k go up to 2, and then to 3, and then to 4, and you never stop, right? So this is a condensed way of writing this. Do you agree? Now, just so you know, I could have also written this, and that would give you the same thing, wouldn't it? Because here we're starting with n being 1, and then 2, and then 3. And I could have really used any letter I want there. Right? So this letter that we use here, this is called our index, and that letter right there is a dummy variable, so to speak, right? We could exchange it with whatever we want. K, N, J, I. Usually we're going to see K, N, J, or I. That's what we're usually going to see, all right? But just be sure you understand that all these mean the same thing, all right? So that is what a series is. It's an infinite sum. Now, let's define something else. A partial sum, what do you think it's going to be? A partial sum is what? Yeah, partial. What do you mean by partial? What do you think we mean? Yeah, we're only going to add up part of the infinite sum, okay? So it's not the entire infinite sum, it's part of it, which means that when we start adding, we actually want to stop somewhere, okay? So a partial sum is a finite sum of a sequence. For example, if I say, okay, I'm going to start my index at 1 of a sub k and stop somewhere, then I don't want to put infinity, right? So I'll put wherever I want to stop. So I could put 10 here or maybe 100, but I'm going to put here n, all right? So it's going to stop at n. So notice I'm using k here, which is the representation of the subscript, and then this is where my stopping point. This right here would be a1 plus a2 plus a3, but then I would actually stop at a sub n. Agreed? This is called a partial sum, but specifically, because we stopped at the nth one, this is called the nth partial sum. That's going to become important, all right? The nth partial sum. Everything pretty straightforward at this point? Okay. All right. Now, I want you to notice something. Notice what would S of 1 be? Oh, I'm sorry, I forgot to write down what sorry. This is also equal to what we call S of n. Sorry, this nth partial sum is this, but we will represent it with a capital S subscript n. So when you see capital S subscript n, that means you're going to take the first n terms of a sequence and add them up, right? So what would S of 1 be? If somebody gave us a sequence, right? Remember, our sequence here is a sub n, right? If somebody said, hey, find the first partial sum, what is that equal to? A sub 1. That's all it is, right? Then what would S sub 2 be? S sub 2. A sub 1 plus A sub 2, right? S sub 3? A sub 1 plus A sub 2 plus A sub 3, right? And if we actually had the sequence, if someone had given us the sequence, then we would actually have numbers in this list, wouldn't we? And we would say, okay, the S sub 1 is just the first number. S sub 2 is the first 2 numbers added. S sub 3 is the first 3 numbers added, right? Get it? And then, of course, S sub n would be what I wrote down over there, A sub 1 plus A sub 2 all the way out to A sub n, right? Okay? Does anybody kind of recognize what we've just created here? I mean, we started with a sequence of numbers, right? And then we defined this thing S sub n. And it was defined to be this thing, right? But what is S sub 1 followed by S sub 2, S sub 3, S sub 4, S sub 5? What have we just created? A new sequence. Haven't we? Haven't we just created a new sequence? We have the original sequence. But now we've created a new sequence. We could look at this new sequence as the sequence S sub n, couldn't we? And it would be S sub 1, S sub 2, right? Like, it would be S sub 1, comma, S sub 2, comma, S sub 3. Make sense? Yeah. Now, we could actually look at this as an infinite sequence also, because, you know, we could stop at n, but you could keep going, right? So this sequence would keep going as long as we want to keep adding things up, right? This sequence would keep going. So this sequence right here, Well, it's a sequence, right? And what did we talk about last class, in last two classes when it comes to sequences? What are we interested in when we talk about sequences? Whether or not they converge or diverge, right? So you have this sequence. It might converge, might diverge, right? What we're interested now in looking at is if we start adding up the terms in the sequence, that new sequence that we create, does it converge to something? Make sense? So let's take a look at, I want to take a look at an example, a visual example. Do you all understand the difference between the sequence A sub n and S sub n? They're very different, right? So here's a visual example. And let's take the sequence, let's take this sequence, put it over here. A sub n equals 1 over n squared. Okay, let's take that sequence right there. Let's list out a couple of the terms of this sequence. First term would be 1, then 1/4, right? Then we plug in 3, 1/9, right? 1/16, dot, 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 right? Now, is this sequence converging to 0? Yes, this sequence converges to 0. I could say that A sub n converges to 0 because, well, if you took the limit and you let n go to infinity, this is a fixed number over infinity, and that goes to 0, right? So that sequence goes to 0, right? Now, let's look at this sequence. Let's look at the sequence S sub n, right? That sequence. So tell me what S sub 1 would be. It would just be 1, okay? What would S sub 2 be? It would be this plus this, right? Which would be 5/4. Okay, S sub 3. 1 plus 1/4 plus 1/9. So what is that? You got to get a common denominator of what, 36 here, right? So 36 over 36, and then 9, what's that, 45? What is that? Is it 49 over 36? Is that right? Yeah, whatever, who cares, right? I'll have the computer verify. But we get a new number, right? And we could keep doing this, right? So S sub n is equal to, right now, this sequence 1, 5/4, we think 49 over 36, comma, dot, 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 right? We know this sequence converged to 0, didn't it? The series of that sequence is a new sequence, right? And this sequence, we want to know if it converges, right? That's what I'm telling you we want to know. So let's look at the graphical situation here. Okay, so first I need to put the sequence in. 1 over n squared. There we go. All right. Make it a little smaller so. Yeah, okay. So let's take a look. What I have here is the plot of the sequence, and then this is the plot of the nth partial sums. It's the plot of that sequence. So we already knew that the sequence was 1, then 1/4, then 1/9, right? And it's converging to 0, right? But when we look at the sequence S sub n, look at that, right? What do we get? First we got 1, right? Then we got 5/4, which is here. Then we got 49, 36, we think, right? And then look at what this one is doing. Is that one converging? Does this look like it's converging or not? Maybe, I don't know, right? We want to know, is it going to a number? So let me do this. Let me get more points in here. And yeah, I'm not going to be able to get any better than that. Okay, so let me get some more points here. So I'm going to go further out. So now I'm going out. I'm like in the 50th, 60th, 70th, 80th, 90th. I'm in the 100th. I'm in the 100th, I've taken the 100th one, right? And now I've added them all up, and look at this, right? Look at that. Let me back this out. Does that look like that's converging to something? Or does it look like it just keeps on growing? It's hard to say, right? Now, my computer's already telling you it's converging, okay? My computer's already calculating it for us. So this sequence is actually convergent. This sequence. This converges to 0, but when you start doing the sums, it starts to converge to 1.634. What does that mean? I mean, what does that mean to us? It means if you take 1 plus a 4th plus a 9th plus a 16th and you start doing that forever, right? Forever and ever and ever. It's never going to get bigger than what, 2 for sure, right? According to this picture. So the series of this sequence is not unbounded. It doesn't become infinite. And that usually causes problems for students because, you know, if we take this and start adding them up, problems in terms of trying to rationalize this. If we start adding these up forever, it's difficult to wrap your head around the idea that if this is a positive number, right, and you're adding that to another positive number, and you keep doing that, right, these are all positive numbers, and you do that forever, like how is it possible that this doesn't become infinite? But it's the fact that these are actually deteriorating fast enough that when you start adding them, that new series that you create converges. Does this all make sense? I mean, this is an important concept here, that you understand the relationship between a sequence and its series. Yeah? Okay. Now, let's try a different sequence. Let's see if we can mess with a different sequence and try and see what it does. Okay? So that was 1 over n squared. Let's back this up a little bit.
So if all we're going to know, it converges to that number specifically.
Oh yeah, that's exactly that's what the next 3 weeks are going to be about. Yeah, this is not, I'm just trying to show you that when you have a sequence, what we're interested in knowing is when you add up the terms of that sequence, does it converge or diverge? Being able to show that is difficult. And that's what we will do. So how we actually get to that 1.6 whatever, hang tight, all right? It's coming. I just want you to see visually what we're trying to accomplish, okay? Now, let's pick another sequence. How about instead of 1 over n squared, how about just 1 over n? So what if we take the sequence, I'll write it like that, 1 over n. Right? That's an appropriate way to write the infinite sequence, 1 over n, like that. And that is the sequence 1, 1/2, 1/3, 1/4, right? And if we start doing the series of those, right, S sub n, then S sub 1 is 1, S sub 2 is the first two added. 1 plus a half, right? Which is 3/2. Agreed? And then S sub 3 is 3/2 plus, I just do 3/2 plus a third. And that's 9 11/6, right? And we could keep going. Now, let me ask you about this sequence up here. This sequence up here, does it converge or diverge? It converges, right? What does it converge to? 0, okay? So just like n squared did, right? This goes to 0, right? Now our question is, what does this go to? Or does it? Like, does that one converge or not? So we start 1, then 3/2, then 11/6. Okay, so let's put it in. I think I haven't done it. 1 divided by n. And here we go. Well, it appears the computer is showing the original sequence goes to 0, right? I am recording? Yes, okay. And then it looks like it's saying that this is going towards 3.776, right? Right? But I've only gone out to like the 30th term of the sequence. So let me start adding some more, okay? So watch what happens. Keep an eye on this number. If I start adding more points, look what's happening. What's happening to that number? It's starting to grow, right? Now I've gone out to I've gone out 100 on my sequence, right? I started adding them all up and it looks like 5.18. So let me now go out to 400 instead. So if I keep going, keep an eye on that number. It just broke 6, didn't it? Okay. And then now let me go out 800. And are we going to break 7? We just broke 7, didn't we? So look at this sequence over here. This sequence is actually looks like it's growing, right? Compared to the other sequence, felt like I was about to break my computer there. It slowed down. Let me go back to this one. That was the 1 over n squared. So it dropped down to 0, but look at this over here. I'm out 800 terms. I've added up the first 800 terms. Oh, look at that. I just don't seem to want to break like 1.6, right? Let me go out even further. 1,200 terms. Still hasn't broke 1.644, right? You see that this shape is a little different than the previous one. It's not growing like that one was. So this is the problem that we are going to run into. We have two sequences that we just looked at, 1 over n squared and 1 over n. They both go to 0, don't they? The sequences themselves go to 0. But their sums did two different things, right? It appears that way. 1 over n squared looks like the sum converged, but 1 over n, it looked like the sum was diverging, going to infinity. So our goal is going to be, I give you a sequence, we create an infinite series out of it, and then we ask ourselves, does that converge or diverge? And to help you do that, we will have all of these tools that we will use. Okay? Everyone have one of these? I printed extras. Anyone need one? Yes? Yeah, right here. It's a $5 donation. I'm taking $5 donations for these. All right. So, I hope that in some way illustrates the challenge, what we're going to try and do. Let me dial this thing back because my computer was freaking out. Okay, and let's look at that cheat sheet, this little thing, and I want us to look at the very first test. These are called tests, and they're tests because it's like you're going to have to look at your series and then run a test on your series to see whether or not it does converge or diverge. So look at the first test there. It's called the Nth Term Test. This test is a very, very easy test to do. It's the easiest test to do on the entire page. The problem with the Nth Term Test is that although it can help and tells you a lot, it's not useful in a lot of situations. So the test says, all right, let's say you have a series, right? That's what it says. So everyone understand this notation? That's what it says there? It's implied here, okay? It's implied that there's an n equals 1 to infinity there, even though it's not written, okay? So it says, let's say we have some series. Now, this series will diverge. That means not converge, right? If what? Diverges if what? The limit as n goes to infinity of a sub n, which is this sequence, right? The sequence we're looking at. If the limit of that does not go to 0, then you are done. You can say it diverges. Now, there's a little comment on the side there. It says inconclusive if the limit does go to 0. So let's take a look at the examples we just did. As an example, if you're asked right now, does this converge or diverge? And I give you some n equals 1 to infinity of 1 over n squared, we know from the picture I showed you that that looks like it converges, right? But if we don't have the picture, could we use this test to see if it does? Well, we just identify a sub n, so a sub n for us is 1 over n squared, right? We take the limit of that. We let n go to 0, or n go to infinity. 1 over n squared, what does that go to? It goes to 0. So what does this test tell us? This tells us if that limit does not go to 0, it diverges, right? If it goes to 0, does that mean it converges? It's inconclusive. This test gets used the wrong way a lot of times, okay? What we're saying here is that sometimes we call the Nth term test the test for divergence, because all this test will ever be able to tell you is whether or not a series diverges. That's all this test can ever tell you. If this limit goes to something other than 0, then it diverges. If it goes to 0, it's inconclusive. Now, you can compare that to this one. I'm just going to put 1 over n. I'm going to leave the limits off. This one right here, if we ran this limit, that limit's 0 also, right? That would be inconclusive. We know this one converges, right? We know this one converges from the picture. We know this one diverges from the picture. And you can see that because the limit goes to 0, that's not enough to tell you. So this test, do you see that it's limiting? I mean, if you go to 0, then you still don't know?
Yeah.
Okay. So when would this test be useful? Let's do an example of one that this test would actually be useful for. So how about we have this as an example? I'm going to ask you, does this converge or diverge? Right now, I don't want to write this over and over and over. Does it converge or diverge? So I'm just going to go C question mark D question mark. Like, does it converge or diverge? All right. So here we go. Sum n equals 1 to infinity of n over n plus 1. So what we'd have to do, since all we really have right now is the nth term test, right, is we would say, okay, I'm going to do the nth term test. Notice I'm letting you know, as the person sitting there, what test I'm about to run. And this is what you have to do, is we start to get through all these different tests. As you're working through a problem, you have to indicate to me or to the reader what it is you're actually doing. So I'm about to run the nth term test, right? That means I'm going to take the limit as n goes to infinity of the sequence, and the sequence is n over n plus 1, right? Now, how would we determine what that is? You'd have to use L'Hopital, right? But you have to change it to a function of x, right? But we know we could do that, right? We could change this to a function of x. We could do L'Hopital. We get 1 over 1, wouldn't we? So this is going to go and converge to 1. Converge, right? The arrow means converge by L'Hopital, right? So I'm just going to state under this by converting n over n plus 1 into f of x equals x over x plus 1 and L'Hopital. See, do you already see like the answer to this problem is more than just like equals 1? You know what I'm saying? Like the answer is what you're putting down on paper that's communicating what you're doing. That's the answer. Now, this limit of this sequence went to 1. What does that tell us by the nth term test? This is not 0, right? That's what the nth term test is asking you to check. What does that limit go to? Well, it goes to something other than 0, right? Therefore, the series n over n plus 1 diverges. All right, does that kind of make sense how I kind of put it all out here? We're going to have to practice as we proceed how we express our thoughts onto paper. And this is an important skill, I mean, because a lot of you want to be engineers, computer science, whatever it is, even biology, doesn't matter what your major is. You're going to work with people at some point in your life. And you're going to need to be able to communicate your ideas. I know you probably do this every day, right? You may have it up here, but you got to be able to communicate it to somebody else. So we have to practice getting our ideas across, all right? That's what I'm looking for. All right, make sense? So that's how this test works. If you get something other than 0, you're in business. So on a test, this always happens. We start learning all these other tests and we realize how difficult these are and we forget about this test. So I give a student a problem on a test and all they have to do is run the Nth Term Test and it comes out to be something other than 0 and then they just say diverge. But they skip that step and they assume that they have to use some other test and then they go through all this trouble and they spend 20 minutes trying to do a problem they could have done in like a minute. Okay, don't forget about this test. It's always the first one you want to use, all right? All right, now, most of the series we deal with in here, most of the series that we are going to investigate here, the sequence inside is going to go to 0, which means it's inconclusive, all right? So let's start talking about the first common sequence. I mean, right now, if someone can hand us a sequence and ask us, and we really can't do anything other than the Nth Term Test. That's all we have, right? And if it goes to 0, we just kind of go, I don't know. So there's certain series that look a certain way that if they look exactly like this, then we can do something. So the first one, I'm going to put here common series. These are ones that you should be able to identify them when you see them. We're going to talk about 3 of them. First one is called a geometric series. The one after that we're going to do is called a harmonic series. And the last one is called a telescopic, or sometimes it's called a collapsing series. Okay, so we're going to investigate these 3 types right now. Sound exciting? All right. So these are ones that when you see them, when someone gives them to you, you go, oh, yeah, that's geometric. Okay? Since it's geometric, here's the conclusion. All right, so let's start with geometric. Okay, here's what a geometric series looks like. A geometric series looks like this. A plus AR plus AR squared plus AR cubed plus AR to the 4th plus ... forever. So what do all these terms of the series have in common? They all have an A, right? So there's some constant in all of them. And then everything else in the series is some power of some number, right? So this is like r to the 1st power. This is actually r to the 0 power next to this, right? There's a little r to the 0 right there. Okay. And then it just keeps going. So can we actually write this in a more condensed form using, I want to use for this one, let's use n equals 1. Is there a way that you can write that series out in a condensed form? It's like, what would the formula here be? A times r to the n. Will n work? N minus 1 will work. Okay, so let's see. Why does that work? If we plug in 1, right, we want to actually get r to the 0. So remember, this right here next to it is r to the 0. Right, so when we plug in 1, we need to get a 0 here. When we plug in 2, we need to get a 1. And when we plug in 3, we need to get a 2, and so on and so forth, right? And you've got an a sitting in front of all of these. So the a is not impacted at all by that exponent. Agreed? That is the form. So all geometric series look like that, which can be written like this. Yes?
You couldn't change the n instead of n equals 1, just the n equals 0. What would happen if you did that?
I'm glad you asked. You want me to use n equals 0 instead?
Yeah, what would happen if you did
And then how would your formula change? Would your formula change?
that? A to the r of n?
It would just be a r to the n, right? Like this? Would that create the same thing? Does everyone agree that this would create the same thing? If I start at 0 and then plug in, I get a times r to the 0, which would be that one. Then I let it go to 1, and it would be that next one. Yes? Now, the reason why I haven't done that is because, you remember, didn't I tell you n had to come from the natural numbers?
Yeah.
And I said 1, 2, 3, 4, 5? Yes?
Yeah.
Now, it turns out, as we proceed here, that this is completely legal, all right? You can start it at n equals 0, but your formula is going to change a little bit, right? And in theory, you can start your index anywhere you want to, as long as it generates that list. Okay, so if I wanted to get like really wacky with it, I could start at n equals 2 to infinity, right? And then I could say a r to the n minus 2, right? Because when I plug in 2, I need to get 0. And then that would work, right? Yes? All of these are equivalent. Now the ones that we're going to see most often, and the ones that you will see in most textbooks, are either this one or in fact this one. I was going to tell y'all this later, but you brought it up, so let's go ahead and let's just put that away right now. You can start your index at 1 or at 0, but you see the difference in the formula. Yes? Okay. Now, as I proceed here with this idea, I'm going to put this one away, put that one away. I'm just going to work with this one, all right? Okay. Now, the question is, does a geometric series converge or diverge, right? Ultimately, we want to know, does it converge or diverge? That's what we'd like to know. So you ready to figure out what it does? Yeah? This is going to be pretty awesome. I think you're going to like this. Okay, so let me start with this. Let me ask you, what would S sub n be? Tell me what S sub n would be. That, for a geometric series, that means the nth partial sum, doesn't it? The nth partial sum, which would mean I take the first one plus the second one plus the third one, right? Squared. Remember, I'm using this formula right here. Right, like that. But if I ask you to only take the nth partial sum, so you're going to stop at n, right? Then I would keep doing this until I get to which one? What would my very last one be? A r to the... what am I plugging in? I'm going to the nth one, right? So I'm stopping at n, so I'm going to just replace that with n. It's already n, right? A r to the n minus 1. Do y'all agree? That's, if I ask you to add up the first n of them, that's what you would tell me, right? Yes, yes? Okay. All right. Now, check this out. I'm going to do something here, and it's not going to seem very natural, but let's just see what happens. And keep in mind, what we ultimately want to know is what happens to this sum as we go out forever, right? As we go out forever. So as n goes to infinity, right, this thing just keeps growing, right? Keeps growing? Yeah. And we want to know what that sum is. So I've actually started adding them up, but I stopped myself at n, all right? Now take this and tell me what would happen if I multiplied both sides of that equation by r. Don't ask me why I'm doing it, though, okay? Just tell me what I would get if I multiplied both sides by r. So this would be this, right? This would be AR. Next one, AR squared. Next one, AR cubed, plus dot, 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 all the way. Now what would that last one be? AR to the n, right? AR to the n. because you're adding 1 basically, right? You're adding 1, you're adding a power, adding a power, adding a power. Adding 1 to that would give you AR to the n. Agreed? Okay. Now I'd like for you to consider this. What's S sub n minus r times S sub n? So what if I asked you to take this right here and subtract this from it? So I'm taking this row and subtracting this row, right? So I would have A, right? And subtract nothing. There's no A here, right? So I would have an A there. I would do AR and I would take away AR, right? I'd have AR squared and AR squared would cancel. And then I would have an AR cubed here, wouldn't I? Yeah. And that would cancel with this one. And I keep doing this. Now what happens at the very end? This is a little bit tricky here. Does this one cancel? Yes, because the one right in front of this is AR to the n minus 1, isn't it? The one right in front of this one is that one. So this one would cancel. Does this one cancel? No. This one does not cancel. So I'd be left with the A here, and then I'm subtracting this row, so minus this one, right? Minus that one. All right. Let's back up just a second. We were trying to figure out what this partial sum was, right? We stopped at n and we said, okay, that's what it is. Then I just, like, out of nowhere, and trust me, I didn't come up with this on my own, all right? Multiply both sides by r. We got that. Then we subtracted the 2. Why? Because someone did this already and showed it to me, and I'm showing it to you. If you subtract these, you get this, right? Now, what is it that we're interested in? We're interested in this, right? We're interested in knowing, like, what is that sum if we add up to n? And then we ask ourselves, what happens if we let that go out to infinity, right? But look at this expression right here. They both have S sub n in them, don't they? On the left side? Let's factor it out. If I factor out S sub n, what would I be left with if I factor it out on the left side? 1 minus r, okay? And then I would have equals, let's factor out an a on the right side. Yes? That's what we would have? And finally, let's solve for S sub n. So let's divide both sides by 1 minus r. Is that all right with you? Okay. Now I know you're seeing this for the first time, and you're kind of just trying to figure out like what's going on here. But this is pretty badass what just happened, all right? Because we had an expression, S sub n, that we were trying to figure out, right? And it had a bunch of things added up together. We wanted to know what would happen if we let this n go to infinity, right? The problem is if we let n go to infinity, these terms we just keep adding more and it just becomes infinitely long, right? But the new expression we have for S sub n, what happens if we let n get bigger? Do we get a bunch of terms adding up? What change, if I start letting n become big right now, what's the only thing impacted by n in this entire expression? Just this. This is the only thing that's going to change. We don't have like this infinite sequence of terms that just keeps getting longer. We get this expression which is only impacted right here. So what happens right now if I take the limit as n goes to infinity of S sub n? What happens if I let n go to infinity now? It would be the limit of this, right? It's a, and then it's 1 minus r to the n, right? Over 1 minus r. What happens as I let n go to infinity on this? So can you tell me what happens to this right here? If n gets huge? It gets huge? Does it? .1, lecture notes from last class. Oh, I can go back one more page. Very bottom of the first page. The sequence r to the n goes to 0 if the absolute value of r is less than 1, right? This is basically asking us what happens if I put a number right here, right? And I start raising it to bigger and bigger powers. If that number is bigger than 1, this thing's going to get huge, isn't it? But if that number is smaller than 1, if the absolute value of that number is smaller than 1, then as I raise it to bigger powers, it's going to vanish. It's going to go away, isn't it? This whole term will just evaporate out, and we'll just get like 1 minus nothing, which will just be 1, right? But it all depends on the size of r. If r is too big, this thing blows up. If r is small enough, it's going to, what? If that goes away, then what's our answer? A over 1 minus r. Do we know what A is? I mean, A was given to us in the sequence, right? Do we know what R is? R was given to us in the sequence. So let me kind of like summarize all this. I hope that this is registering in your brains. There's not many series out there that we can do this with, all right? Yes?
The one thing that's weirding me out is right where you wrote a to the r of n minus 1
A to the R.
on the second line, and then plus, to your left, in the middle.
When you cancel it.
When you canceled it from the top.
Yeah.
So you wrote a times r to the n minus 1 right before the last of a to the r to the n.
Yeah.
Right. So you brought that down because since that was the last one from the top, you're saying that this is going to be before the last on the second one, correct? Yeah.
Yeah, I was taking this row and subtracting this row. So when the first term I had here was an A, and there's no A by itself here.
Right.
So there's nothing to kill that A off. Okay, so I had to leave it. Then it was AR. AR canceled because I had one here and here. Then AR squared canceled because I had one here and here. And I keep on going down, and I get to A times R to the n minus 1. So let's say that's A to the 9th, okay? This is going to be A to the 10th, or AR to the 10th, right? This is AR to the 9th. This is AR to the 10th. This, right before this one, would be AR to the 9th. So those two would go, right? This one wouldn't, though. But you're subtracting this row, which is why it's minus. Does that make sense?
That makes more
Okay. All right, so here's where we are. We have pulled ourselves to a very, very nice conclusion. All right? And it's actually summarized right here for you on the second one we have there. Look at that. It says that if you have a series that is geometric, so looks like AR to the n minus 1, then it will converge. It converges, right? And it actually tells you what it converges to. What does it converge to? S equals, so S meaning the sum of that series is actually A over 1 minus R, so long as the absolute value of R is less than 1. Do you understand where that comes from now? This comes from the idea that if this R is the absolute value of that is less than 1, then that goes away and you're just left with A over 1 minus R. And that is the actual limit of that sum. That's where it's headed. Okay? But if you have the other case, it diverges if the absolute value of R is, now they say greater than or equal to 1. Why do you think they're including the equal? Why would it diverge if R was 1? What if this was 1 right here? What's 1 to any power? 1. So wouldn't this just be A? And so you'd be adding A plus A plus A plus A plus A plus A plus A forever, right? And that would just get huge. It would be like adding just the same number over and over and over forever. That number is not getting smaller, is it, right? It's just staying the same. So that would diverge. I'm not sure what the looks on your face are all about, if it's good or bad, or you're just tired, or... Let's do an example. I think it's time to figure out if we can see a geometric series. Okay, let's try this one. Oh, you know what? Before we do this, let me just clarify one thing. if S sub n is the sequence of partial sums then if the limit as n goes to infinity of S sub n equals S, then the series converges. All right, so all this is saying is that if we can find a formula that represents the partial sums and then take its limit and let it go to infinity, if we get an answer there, that's what the series adds up to be. So we just did that. We had the geometric series, right? We looked at the nth partial sums. We did this really clever algebra that gave us a formula for it, and then we took the limit and let n go to infinity. If we do that and get an answer, then the series converges. So I'm gonna leave that there while we look at this example. So how about this series, everyone? I want to know if this converges or diverges. Sum, let's use k. K equals 1 to infinity of 4 to the k plus 1 over 5 to the k minus 2. All right, what's the first thing we should try here? Probably the nth term test, right? Try the nth term test. All right, if we do the nth term test, what happens? Just let's think about it. If we do the nth term, right, we have to take the limit of this, right? As in this case, as k goes to infinity, because I'm using k. So if I take the limit as k goes to infinity of 4 to the k plus 1 over 5 to the k minus 2, what would happen? The top would go to what? Infinity, and the bottom would go to infinity, right? And then we would probably have to try maybe L'Hopital. No, thank you, right? What's that? Yeah, that would be messy with the L'Hopital, wouldn't it? Okay. Shoot, man. All right. I really don't want to do L'Hopital on that. So I'm going to start doing algebra on it. Is that the same thing? Just using properties of exponents here. Now, when we learn properties of exponents, we usually learn them this way. Like we start with this and we put these together, right? And you say, oh, I'm going to put those together and add the exponents. So you do k, and then you add the negative 2 to be k minus 2, right? Put those together, you get k plus 1. We're going to be doing a lot of pulling them apart the other way now. So do y'all agree that's the same thing? Okay. And then this is equal to the limit as k goes to infinity of, check this out, 4/5 to the k times 100? Where did that come from? 5 to the negative 2, I can bring it up as 5 squared. 5 squared is 25, right? 25 times 4 is 100, right? Okay, so that's what we got. What happens now? Can I do this limit? So what does it go to? Apparently this is not burning into your brains very well. This power is getting big, right? This number is being raised to a power that's getting bigger. It's going to get smaller. Why? Because 4/5 is smaller than 1, right? This number is smaller than 1, so when we raise it to a power that gets big, the number goes away, it starts to go to 0. So this is headed to 0, right? And 0 times 100 is still going to give you something very small. So this is headed to 0. Do we all agree?
Yes.
Okay, so what can we conclude? The nth term test tells us that the sequence, right, goes to 0, and therefore
Converge.
we know nothing. All right? But I'm glad you said converge, because that's the mistake we don't want to make. The nth term test is a test for divergence only. You should never run an nth term test and come to the conclusion of convergence. That'll never happen. You can only conclude divergence. So if this would have gone to, let's say, 2, we would be done. We would say diverge. But because it goes to 0, it's inconclusive. All right? It's an inconclusive test.
If it's not divergent, then it has to be convergent. Those are the only options, right?
No, this doesn't say that it's not. This.
Oh, okay, it could be divergent still.
That's right. It could be divergent. Yes, it could be divergent, right? It could be. But this test says if this limit does not go to 0, it has to be divergent. The only way I can maybe explain this is, let me see. Now, I do not want to get into a political debate. This is probably not the right time of the year to bring this up, or right time in our society right now. But if you physically are standing in Texas, I'm not going to say if you're from Texas or if you're a Texas citizen. I'm just saying if you're physically standing in Texas, all right, regardless of how you got here, then are you standing in the United States of America? At least right now you are, right? Do you agree with that? So if you're from Texas, then you are, or if you're in Texas, you're in the United States. Now, does this work the other way around? If you're standing in the United States, are you standing in Texas? Now, could you be standing in Texas? Yes, but this is not a strong enough condition to say you're from Texas, right? You still could be. So this is kind of what's happening here. We're saying if this thing goes to something other than 0, you're definitely divergent. But if it goes to 0, that's like saying you're in the United States. You don't really know. You could still be from Texas. You could diverge. You could converge. Does that make a little more sense? Okay. All right. So we're not done, right? We haven't answered the question. All we know is nothing. Okay. So don't sit here and say, and I know this happens every semester, students will be like, this means convergence. It does not mean convergence. It means we don't know. Okay. So what are we left with? Well, I hope with what we just did, you see that this is a geometric series. If we rewrite this, we could rewrite this as sum k equals 1 to infinity of 100 times 4/5 to the k. Now, I did that work already when I was doing my nth term test, didn't I? I did that work. But if I look at it like that, then do you all see that this is always 100? So that's like the A. And then here we have R, right? And then raised to the K. Do you agree? Yeah? You sure y'all see that? You see a number out front. You see another number that's being raised to a power. That's the form of a geometric series. Geometric series, all geometric series look like this. AR to the, n minus 1, I'm using n here. So does this and this match right now? Yes or no? No, what's wrong? In this formula, right? In this formula, we have an n minus 1, don't we? In order for this to match this exactly, that would need to be a what? A k minus 1, right? So watch, more magic. Is this the same? Can I just do that? I can't do that, right? I'm not allowed to do that, but I'm allowed to do that. Right? I can subtract and add 1, can't I? Okay.